This is the last major piece of our discussion of linear algebra, eigenvalues and eigenvectors. This is one of the really important pieces from the perspective of quantum mechanics. Over the past lectures, I've probably said eigenvalue or eigenvector or eigenstate without really thinking about it or noticing. So it's important to understand what these things are, and they will be used extensively throughout our discussion of the mathematical formalism of quantum mechanics. Essentially, what eigenvectors and eigenvalues are special vectors for a transformation. Suppose, for example, I have Cartesian free space, say x-coordinate, y-coordinate, z-coordinate, x-axis, y-axis, and z-axis. If I consider a transformation that is rotation about the z-axis, for instance, a vector here in the xy plane would be rotated around, say, to point in some other direction, remaining in the xy plane. A vector that points along the z-axis would remain unchanged, whether it's pointing upwards or downwards. These vectors that are unchanged in a transformation have some special status, and it's not simply, for instance, the vector that points along the z-axis in a transformation like a rotation like this. You can think, for instance, suppose I have just 2 dimensions now, and consider a transformation that takes like a box shape like this and maps it to something that's skewed, stretched out in the x direction and smooshed over in the y direction. If I had a transformation like this, you can probably imagine what one of the vectors that remains unchanged would be. It points along the x-axis. And it's not going to remain unchanged, but it's going to be extended slightly. It's going to point in the same direction. As opposed to some other vector, which for instance points in, say, this direction, and it's going to be extended and shifted over. So the blue vector here is not unchanged. The orange vector, however, is essentially unchanged. It points in the same direction. There's actually another vector in this transformation that remains unchanged, and it points sort of off in this direction. That vector actually legitimately remains unchanged. It is neither extended nor contracted. You can think about this transformation as taking your x-coordinate and multiplying it by some value. The y-coordinate remains unchanged, but the x-coordinate also depends on the y value. The higher up you go, the further over you get shifted. And if you're lying along this vector, the fact that you get shifted over in x and the fact that you're along a line, you're essentially along a line where the amount that you have moved up in y counteracts the amount that you're shifted over in x, and you end up essentially back where you started. So these special vectors are called eigenvectors, from the German prefix eigen, which means self or proper. So these are the self values or the proper values of a transformation, the values that return to themselves in some sense. And the amount, for instance, by which this orange vector gets increased in length or decreased in length is the eigenvalue. More formally, what we're looking at are equations that involve transformations. So, as before, t hat will represent my transformation, and I will write vectors associated with the space that we are interested in as kets in bracket notation. Your eigenvalue equation fundamentally then is your operator acting on your vector gives you some eigenvalue, lambda, times your original vector. So the action of your transformation is to return a scaled version of the vector that you started with. Since most of what we're going to be talking about in this lecture is what happens when we represent a transformation in a particular basis, you can think in terms of matrices. The matrix T acting on the vector A gives you back the eigenvalue lambda times the vector A. And we can rewrite this a little bit if you think about trying to bring the right-hand side over to the left-hand side. You would end up with T acting on A minus lambda multiplying A, lambda just being a scalar, not a matrix or a vector or anything. And if I want to factor A out of this expression, I can write this as the matrix T minus lambda times the identity matrix, all acting on A as a matrix. So this is going to be equal to 0, as is this. And this is the sort of equation that we're going to be considering when we talk about finding eigenvalues. So lambda is our eigenvalue, and A is our eigenvector. I haven't said why these things are interesting yet. Mostly they're interesting because they tell you what the core properties of the transformation are. These are sort of the most interesting facets of a transformation. And when it comes to quantum mechanics, we'll see that these things are actually very important. So bear with me while we go through some of the mathematical details. If what you're interested in doing is finding eigenvalues, the easiest way to think of it is in terms of that expression. We're working with a matrix equation, t minus lambda times the identity, multiplied by some vector, is equal to 0. You can imagine trying to solve this by standard techniques involving matrices. For instance, if I called this matrix A, I would have capital A acting on A is equal to 0. And I could solve this by left multiplying by the inverse of A. I can multiply by inverse of A over here, and by inverse of A over here. The right-hand side, of course, is going to remain 0. The matrix A, no matter what it is, acting on the 0 vector, will give me 0. But on the right-hand side, I'll end up with the identity here, and I'll just end up with A equals 0. This was not particularly informative. It didn't tell us anything about A. The reason that we can have these vectors that are unchanged by transformations is that it's actually impossible to solve the equation like this. This doesn't work. The reason this doesn't work is that if we have A not equal to 0, the only way this equation can have a solution is if the determinant of t minus lambda identity is equal to 0. So our actual equation to determine the existence and value of an eigenvalue is this equation. That's what we're interested in. The determinant of the matrix t minus lambda times the identity equals 0. This is an equation that we can solve for lambda. And if we solve it for lambda, we'll find the eigenvalues. We won't find just one solution to this equation. We'll find many solutions. If this is an n by n matrix, this equation is an nth order polynomial in lambda. So if we have an nth order polynomial, we're working with complex numbers, we have n roots, so we have n eigenvalues. These eigenvalues are not necessarily distinct, but we should have n of them. So whatever the dimension of our space is, whatever the size of our matrix is, we should get that many eigenvalues. So the best way to see how solving this process actually works is to go through an example. So find the eigenvalues of this matrix, 1 minus I minus 1. There's some special structure to this matrix. If you recall back to when we were talking about the properties of matrices, if I take the transpose of this matrix and the complex conjugate, I find that I have my original matrix back. The I and minus I will exchange places, but then I will be exchanged for minus I again when I take the complex conjugate. So this is in fact a Hermitian matrix, and Hermitian matrices have some nice properties from their eigenvalues that we'll talk about more later. But for now, let's figure out what finding the eigenvalues actually looks like. We're looking for an equation of the form matrix A multiplied by some vector, and I'll just leave it as vector A, equals lambda times our vector A. And I told you that you could solve this by moving this over to the left-hand side and trying to solve for the determinant of your matrix under those circumstances being equal to 0. That's what's called the characteristic polynomial, the equation, the characteristic equation. The determinant of 1 minus lambda minus I minus 1 minus lambda is equal to 0. That's our characteristic equation. That's what we get when we rewrite this as A minus lambda times the identity matrix multiplied by A equals 0. And this matrix is what we're taking the determinant of. So you know how to find the determinant of a 2 by 2 matrix. It's just something that you can write down. It's 1 minus lambda, this term, times this term, which I'm going to write as minus 1 plus lambda. And then I subtract from that this term times this term, I times minus I. And that's all going to be equal to 0. If you expand this out, you end up with minus 1 minus lambda squared from these two terms, minus 1 from this equals 0. So the actual equation you have to solve in this case is pretty easy. Lambda squared equals 2. What that means is that our eigenvalues, lambda, are equal to plus or minus the square root of 2. So we have two eigenvalues, plus and minus the square root of 2. So we found our eigenvalues. What about our eigenvectors? The best way in general to solve for the eigenvectors is to go back to this equation, substitute in the value of the eigenvalue, and solve the system of linear equations that results. So let's see what happens when we do that. Given this is our original matrix, let's suppose we have just the eigenvalue root 2. Let's just work with finding the eigenvector associated with the eigenvalue square root of 2. Our linear system, as before, a times some vector a equals lambda times a, can be reduced to a minus lambda times the identity matrix times a equals to 0. So let's just write our system like this. We have our matrix A minus lambda, which we now know is the square root of 2. So when I substitute that in here, I get 1 minus the square root of 2 for my upper left element, minus I, unchanged, for my upper right element, I for my lower left element, again unchanged, and minus 1 minus the square root of 2 for my lower right element. This is my matrix, and it will be multiplied by some unknowns, say x and y. So I can expand out this matrix vector product and get a system of equations that I can solve. For the first equation, I get 1 minus the square root of 2 multiplied by x minus I y equals 0. For the second equation, I get I times x minus 1 plus the square root of 2 y equals 0. And if, for instance, I rearrange this equation, which tells me that x is equal to minus 1 plus the square root of 2 y, minus I times 1 plus the square root of 2 y, and substitute this into this equation for x, what I end up with, and I'm writing it in the margins because you'll see this doesn't actually work, I end up with minus 1 minus the square root of 2 times 1 plus the square root of 2 times I y minus I y equals 0. And if you expand all this out, you find 0 equals 0. Effectively, I get Iy minus Iy equals 0. So it didn't actually tell me anything, but we knew that was going to happen because we set lambda such that the determinant of this matrix was 0. So this system of equations does not uniquely determine a solution. It does actually determine the direction. Essentially, these represent two parallel lines that are overlapping on top of each other, and the direction of those lines is interesting. And the easiest way to figure out what the eigenvectors is, then, is just to take one of these equations and substitute 1 in for x. And if you do that, you can just write down the vector more or less. You find that the vector is 1, and then solving a single one of these equations, substituting in 1 for x, you can see you're going to get something like minus Iy, and then in the denominator you're going to get 1 minus root 2, and then in the denominator you're going to get minus I. You end up with I, say, root 2 minus 1. That's actually your eigenvector associated with the eigenvalue square root of 2 for lambda. If you repeat this procedure with lambda equals minus the square root of 2, our other eigenvalue, you get more or less the same sort of structure. Again, an algebraic system of equations that cannot be solved. It just ends up looking slightly different. And you have 1, and then minus I, 1 plus square root of 2. Sorry for writing so small here. But the overall procedure for finding eigenvectors, at least by hand, for small matrices like this, it is most easy to substitute in the eigenvalue that you found by solving the characteristic equation, setting the determinant for this matrix equal to 0 and solving for lambda, then getting a system of equations that is singular, and doing your best to solve the singular system of equations, substituting in a variable as needed. Given this discussion of eigenvalues and eigenvectors, it's useful to consider the concept of diagonalization. The eigenvalues have this special property where they are mapped back to themselves by your transformation. And it turns out that we can use these eigenvalues and eigenvectors to make a change of basis that converts your matrix into a diagonal matrix. This process is called diagonalization. To see how this can happen, consider I have some transformation A. I can express A in any basis, really, and I'll consider two bases, just any old basis, and then an eigenvector basis, where I mean finding the eigenvectors of the transformation A and using those eigenvectors as basis vectors. If I express the matrix, or the transformation A in any old basis, I'll just call that the matrix A, whereas in the eigenvector basis, I'll call that matrix A prime. Let's think about what A prime does. A prime, as any representation of this transformation will do, it will take an eigenvector alpha, and, sorry, I should write these as vectors, not kets. This transformation A prime will take a vector A and return lambda multiplied by the same vector, a scaled version of the original vector. If I consider what A prime actually looks like, and what A actually looks like, this eigenvalue equation will only be solved, suppose, say, I have A1 and eigenvalue 1, where lambda 1 is the eigenvalue, the first eigenvalue, and A1 is the associated eigenvector. In the eigenvalue basis, which is where we're expressing A prime, I'll just leave A prime blank for now. What does our eigenvector look like? Well, we're expressing an eigenvector in the eigenvector basis. So the eigenvector basis, if this is, say, two components, lambda 1 and lambda 2, lambda 1 and eigenvector 1 would constitute the first component. So I'll have some number here. I'll just call it, well, I'll just say 1. Whereas the component in the direction of the other eigenvector would be 0. We just have a single eigenvector here, and we have no contribution from any other eigenvectors. If I act with A prime on this, I have to get lambda times our original vector back. This also has to hold if I, again leaving A blank, use the other eigenvector. I have to get the same sort of equation, 0 lambda, where this now, let's say this is lambda 1 and this is lambda 2. First eigenvector, second eigenvector. So my first eigenvector, written in the eigenvector basis, is very simple. My second eigenvector, written in the eigenvector basis, is simple as well. And the matrix that works here has lambda 1 and lambda 2 on the diagonal, and zeros off the diagonal. Lambda 1, 0, 0, lambda 2. And you can see that this matrix works pretty well. And this matrix has the nice property that it's diagonal. It's much easier to work with diagonal matrices than non-diagonal matrices. So what we're looking for now, knowing that A prime is diagonal, if I express my transformation in an eigenvector basis, I need to make a change of basis. Typically, what you won't be given a transformation, you'll be given something like a matrix, and it won't be written in the right basis. So you need to make a change of basis. So we're looking for some change of basis that gives me A prime in terms of something, and I'll write it as S inverse times the original matrix that you're given times S. If you consider this acting on a vector in the eigenvector basis now, what S has to do is convert from the eigenvector basis to the basis of our original matrix A. So if I have a transformation that goes from my eigenvector basis to the basis of A, I can actually just straight write down that basis. And write down that transformation, that matrix. And what it looks like is your first eigenvector as a row, and then your second eigenvector as a row. This is now going to take your first eigenvector, for instance, if I write it as 1, 0, or 1, 0, like this, and what it's going to give you is v1 as a vector. So you have your vector v1. That's your result. It does the same sort of thing for v2. So this takes components expressed in your eigenvector basis and expresses them as the eigenvectors themselves. This is exactly what we want our change of basis matrix to look like. So if I make this matrix, this is my matrix S. A matrix constructed with rows given by the eigenvectors of your original matrix A. So we can take a matrix A in any basis, provided it has the right properties, find the eigenvalues, find the associated eigenvectors, and construct the matrix S, which, when multiplied by A in this format, will go from your eigenvector basis to the basis of A, allow A to act, and then convert back to the eigenvector basis. And we know that that has to have this diagonal form. So A prime is equal to S inverse A S, where S is given here, and it has this form, lambda 1, lambda 2, dot, 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 up to lambda n, with zeros off diagonal. So we have our eigenvalues along the diagonal, and we have zeros off diagonal. This is the process of diagonalization, and it will end up being a major component of quantum mechanics, since the process of finding the eigenvalues and the eigenvectors is associated, and we'll talk more about this later, is associated with the process of finding the stationary states of the Hamiltonian, for instance, if the transformation we're considering is a Hamiltonian. We'll of course talk more about that in detail, but for now, the last topic is Hermitian transformations. Hermitian transformations have a lot of nice properties which can only really be expressed in terms of the eigenvalues and the eigenvectors, which is why I put off their discussion until after we had discussed eigenvectors and eigenvalues. But to recall, a Hermitian transformation, we described it in terms of matrices. A Hermitian matrix is a matrix such that the Hermitian conjugate of the matrix, which is equal to the complex conjugate, transpose and complex conjugate of the matrix, is equal to the original matrix. There's another way of defining this, and in terms of transformations, the best way to think about this is as an inner product. Suppose I have some vector alpha, and I'm going to take the inner product of that vector with the product of what I get when I apply some transformation A to a vector beta. If a transformation is Hermitian, we have that this is equal to A hat acting on alpha, inner product with beta. Sorry, this is not just A hat, this is the Hermitian conjugate of A hat. So if we allow our transformation to act on the vector on the right of the inner product, versus we take the Hermitian conjugate of the vector A, or the transformation A hat, and allow it to act on the vector on the left of the inner product. This is the essence of taking the Hermitian conjugate of a vector. If we take this transformation and allow it to act on the right, we could equivalently take the Hermitian conjugate and allow the transformation to act on the left. So in terms of matrices, you can think about this sort of inner product, which is really poor notation because this A hat beta ket is not necessarily meaningful. You have to think about A hat, the transformation acting on the vector beta. But what this actually ends up looking like in terms of matrices, if we express something in a basis, we have the bra alpha, which let's just write that as A dagger. And then we have some matrix, and I'll use capital A, representing our transformation, A hat. And then that's going to act on the vector B, which is taking the place of beta here. I can equally well express this as the Hermitian conjugate of the matrix, which I keep writing as T, the matrix A, acting on the vector A, and that acting on B. So that's essentially equivalent to this notation. Taking the Hermitian conjugate of a matrix and letting it act on the left is essentially taking the Hermitian conjugate in this context. So what this actually looks like, the Hermitian conjugate now of a vector is, well, it's a complex conjugate transpose. So instead of having a column vector here, we have a row vector. Our matrix A is a matrix, as always, and B, not being Hermitian conjugated, is a column vector. When I take the Hermitian conjugate here, you can think about this as being your matrix, which is now Hermitian conjugated, acting on the vector A now, and then when we're done with that, we allow it to act on B. So I can take this sort of matrix vector product, and I can take this sort of matrix vector product, and everything is okay. So an operator is considered to be Hermitian if A dagger in the matrix context is equal to A, or equivalently if it doesn't matter if I allow this transformation to act to the right or to the left. It's a very useful property to have, and Hermitian properties have some, or Hermitian transformations have some really nice properties. If we have a Hermitian matrix, or a Hermitian transformation, or a Hermitian operator, depending on whatever terminology you choose, the eigenvalues of this matrix are real. And you can see that by looking at the expression, say I have some vector alpha, and I will then use Hermitian operator t acting on alpha as well. This, you know what t does to alpha. If we have the state, if alpha is an eigenstate, we have this sort of expression. So I know what t does to alpha. It gives me lambda times alpha. But if this is Hermitian, I can of course pull the lambda out and get the inner product of alpha with itself. If t is Hermitian, I can also allow this to act from the left, like so. These would then be equal to each other. And, well, again, you know what t does to alpha. It gives you lambda times alpha. But now we have lambda left multiplying something. And on the left here, we're dealing with a Hermitian conjugate of our vector. So essentially we have to complex conjugate lambda. So we'll end up with lambda star, and then alpha inner product with alpha. So if these two are going to be equal to each other, lambda equals lambda star, we know the eigenvalues of this transformation are real. The next key fact about Hermitian transformations is that the eigenvectors from distinct eigenvalues are orthogonal. And you can see that by much the same sort of reasoning we applied up here. Consider some eigenvector alpha, inner product with some Hermitian transformation acting on some other eigenvector beta. If I allow t to act on beta, I will get the eigenvalue associated with the eigenvector beta, alpha, and I'll call that mu. So this is going to get me mu times alpha inner product with beta. If t is Hermitian, I can just as easily as before allow t to act on alpha, t hat alpha from the left. And when I allow t to act on alpha, I end up with the eigenvalue associated with alpha, which I'll call lambda. So we'll end up with lambda alpha inner product with beta. As before, I can pull out the lambda here, but since I'm now on the left with the bra instead of the ket, with the Hermitian conjugate instead of the vector itself, I end up with the complex conjugate of lambda times alpha inner product with beta. If these two things are going to be equal to each other, and mu not equals to lambda, or mu not equal to lambda star, this can only be true, this can only happen if alpha inner product with beta is equal to 0. This is really nice because this tells you that the eigenvectors are orthogonal. And if you're thinking ahead, you think orthogonality is a really good property for basis vectors to have. And if you have an orthogonal basis of eigenvectors, then your transformation has a really nice form as well. The final property is that the eigenvectors span the space. And this is sort of true, but there's some caveats. Unfortunately, or fortunately, sorry, the caveats are not really all that important for quantum mechanics. If you have a transformation with n eigenvalues, and they are n distinct eigenvalues, you're guaranteed that the n distinct eigenvectors will span the space. Since if I have a space of dimension n, my matrix that is expressed in some basis, the matrix representation of my transformation will have n eigenvalues, and I will get n distinct orthogonal vectors. And the only way you can have n orthogonal vectors in an n-dimensional space is if they span the space. So those are some of the nice properties of Hermitian operators. This was a lightning quick review, hopefully, of linear algebra. We will work with some of these concepts in more detail later. But for now, to check your understanding, here is another matrix, different from the one that I worked with. It's also 2 by 2, so these calculations are not terribly difficult. Your task is to find an eigenvalue and its associated eigenvector. Since this is a 2 by 2 matrix, and if you look, this matrix is also Hermitian, you know it's going to have 2 real eigenvalues, and the eigenvectors should be orthogonal, and you can go ahead and check those properties as well. But for now, just find an eigenvalue and its associated eigenvector. We'll be doing this sort of thing in the context of quantum mechanics, even with systems as simple as two-state systems where you have 2 by 2 matrices later. This is the last major piece of our discussion of linear algebra, eigenvalues and eigenvectors. This is one of the really important pieces from the perspective of quantum mechanics. Over the past lectures, I've probably said eigenvalue or eigenvector or eigenstate without really thinking about it or noticing. So it's important to understand what these things are, and they will be used extensively throughout our discussion of the mathematical formalism of quantum mechanics. Essentially, what eigenvectors and eigenvalues are special vectors for a transformation. Suppose, for example, I have Cartesian free space. You can probably imagine what one of the vectors that remains unchanged would be. It points along the x-axis. And it's not going to remain unchanged, but it's going to be extended slightly. It's going to point in the same direction. As opposed to some other vector, which for instance points in, say, this direction, and it's going to be extended and shifted over. So the blue vector here is not unchanged. The orange vector, however, is essentially unchanged. It points in the same direction. There's actually another vector in this transformation that remains unchanged, and it points sort of off in this direction. That vector actually legitimately remains unchanged. It is neither extended nor contracted. You can think about this transformation as taking your x-coordinate and multiplying it by some value. The y-coordinate remains unchanged, but the x-coordinate also depends on the y value. The higher up you go, the further over you get shifted. And if you're lying along this vector, the fact that you get shifted over in x and, say, x-coordinate, y-coordinate, z-coordinate, x-axis, y-axis, and z-axis. If I consider a transformation that is rotation about the z-axis, for instance, a vector here in the x, y plane would be rotated around, say, to point in some other direction, remaining in the xy plane. A vector that points along the z-axis would remain unchanged, whether it's pointing upwards or downwards. These vectors that are unchanged in a transformation have some special status, and it's not simply, for instance, the vector that points along the z-axis in a transformation like a rotation like this. You can think, for instance, suppose I have just 2 dimensions now, and consider a transformation that takes like a box shape like this and maps it to something that's skewed, stretched out in the x direction and smooshed over in the y direction. If I had a transformation like this,